Let's look at what are called couples, which is kind of a funny name, but that's what they're called. Sometimes I call these pure moments because this is a kind of a second way to create a moment, a little different than what we've been looking at here so far. So let's have a look at this. So this is another way that moments can be generated. I'm on page 330. Oh, the other thing I'll mention is on page 325, there's a flow chart for 3D operations. I don't know if that's helpful to you or not, but that's on page 325. I remember one year somebody requested that of me, so I cooked it up. So there you go. So that's page 325. Okay. Let's have a look at page 330. You see, if you're going to open this valve, what you're going to do is you're not going to exert a force on it so much as you're going to twist it. So you're going to grab that handle and just turn the handle. You're not going to push the valve to the left or right or in towards the wall or out towards the wall, unless you're under the age of 16 or so, because I remember my dad telling me once that kids don't sit in chairs, they attack chairs, is what he told me. So sometimes younger people kind of grab things and wrench them all around, but hopefully you're just turning the valve. That's all you're doing, right? So this is another way to create a moment. See, there's a couple doorknobs, and if you want to open that door, here you create a moment that's similar to what we've been talking about here so far. I don't know which way you turn that handle, it may not matter, but you'd push on the handle, and what you have then is a force and a distance, right? So you're actually pushing the handle down as you turn it. This knob, you just turn it, you just twist it. You're not pushing the knob any particular direction, you're just twisting it is all you're doing. All right, now what's happening there when you twist it, if you look in the let's say the stem of that valve, the shaft that goes down to actually turn the valve, is there's a lot of forces in there, okay? But for every one on the left, let's say I got one going down, I got one on the right going up. And for everyone on top going to the left, I got one on the bottom going right. And I've got this one and I've got another one that does the exact opposite thing on the other side. So I've shown, I think it's 8 forces here, but you could have 8 million or 8 billion or however many, but they're all equal and opposite on either side of the center of the valve stem. So there's lots of little forces in there, but they all cancel out. So the net force is 0. And what you end up with is just a pure twist. Okay? Now the simplest expression of this is what they call a couple, meaning 2 forces that are equal and opposite. So if you want to know the moment that these 2 forces cause, and that's why they call it a couple, because that's the simplest way to represent this, what you do is you look at the parallel forces that are equal and opposite, and you look how far apart they are, and you just multiply that together is what you do. Okay? And what you get when you do that would be the force times d over 2, because that's the distance to point O from the top force. And then you have the bottom force, and it also has a moment arm of d over 2. And both of those would twist clockwise about O. So what you end up with then is the force times the distance. So the general formula for a couple is moment is force times distance. The distance then is perpendicular between the 2 forces. Now, if you're doing a cross product, you could just say M is R crossed with F. You could do it that way too, if you want to do it in a more vector sort of form. Okay. All right, so there's lots of places where we see these couples applied. You could twist the handle on the valve, as we just were looking at with the doorknobs. You could push down on the doorknob here, or you can twist the doorknob. They have the same effect as far as the moment goes, though a different effect because this has a force applied. That does not. That's just a twist. Okay, 2 ways to open a jar. You can just twist it, or you can apply a force at a distance. Okay, so a number of examples of this. Okay, you can just push on the wrench, or if you have the old T-bar style wrench, you can have 2 equal and opposite forces. There's a really very good example of what they call a couple there. And you could twist that nut off of there. Okay. So this is another way to exert a couple, or a moment, I guess would be a better word. Now let's look at the math on this a little bit. Let's have a look at this object, and let's find the moment that's exerted about different points by that one couple. So what I have here is a couple of 300 newtons going either direction, and it's 3 centimeters on either side of point A. So if I want to find the moment about A, I would take the top one, 300 times 0.03 meters, plus the bottom one, 300 times 0.03 meters. Notice they both turn counterclockwise. And add those up, and I'll get 18 Newton meters. Okay. Now the interesting thing is, that's the moment about A, and that's kind of the point we think about in between the two forces. But I could take moments about any point on that object. Let's look at B, 4 centimeters down below that bottom force, and I'll have 300 newtons times 4, 3, and 3 makes 10 centimeters. That's going to go counterclockwise, 300 newtons times 0.1 meters. Now I have the one above, that's going to come around clockwise, and that has a moment arm of 4 centimeters, 0.04 meters. So that clockwise will be a negative. So I got 300 times 0.1 meters for the top one, minus 300 times 0.04 meters for the bottom one, and the difference is 18 Newton meters. Oh, okay. Could do the same thing here about point C if I was interested in doing that. So I could go to point C, take the moment about C. I got the top one, 300 newtons times 5 and 4 makes 9, 3 and 3 makes 6, 6 and 9 makes 15 centimeters. So that's 300 times 0.15 meters, counterclockwise, so that's positive. And now I've got the bottom one, 300 newtons, 5 and 4 makes 9 centimeters, that's 0.09 meters. That's negative because it's clockwise. So 300 times 0.15 is 45 Newton meters. Take away 300 times 0.09, 27 Newton meters. You get 18 Newton meters. So are you seeing a pattern there? There's a pattern, and the pattern is that it doesn't matter where you take moments about on that object. It will always be the same. It'll be 18 Newton meters. Okay? So that's kind of the deal with this, is any point on the object has the same moment caused by that couple. Okay? So the couple twists the entire object with 18 Newton meters of moment. The moment caused by the couple is independent of its position. That's the bottom line there. Okay? Now, couples can be shown in many ways. There's lots of ways to write them out. Two parallel forces in opposite directions can be used. Any orientation, as long as they're parallel and an object in different directions. Looks like I forgot some arrowheads on this one. Doing that and that. You could also just show it with a twisting arrow. Positive is counterclockwise, negative is clockwise. Okay. Couples are additive. So I've got 30 Newton meters positive, 40 Newton meters negative, 50 negative. So that's a net moment on that rectangle there of negative 60 Newton meters, meaning clockwise 60 Newton meters. They're just labeled at the top, and those are just the values that I know those couples to be. So I'm just using the different symbols, some of the different symbols for couples. So you just label it with its magnitude. That's about it. All right. So it's just another way to generate a moment. Yeah.
How do you know B is negative?
B is negative because if you look at those two forces, if you look at how they twist about a point in the middle, they'll twist clockwise, which is negative. Okay. So I kind of put a point in the middle is how I determine the sign on those double arrow symbols. Okay. Okay, now the couple, there's a few things about couples to kind of understand. The first thing is that it affects every point on the object equally. So let's say I've got a car, and I've got, if it's a front wheel drive car, I'm on that rear wheel, and I'm going to apply that moment to the jack. Now, you shouldn't do this, but let's say I've got the wheel up in the air, and then I start to turn that wrench. What's going to happen to the wheel if I do that? Start to spin, right? Where am I applying that couple about? I'm applying it about the nut, right? But it ends up affecting the axle bolt, the bolt on the axle. So even though I apply the couple over there, it affects the wheel about that central nut there, and the wheel spins. So there's an example of how this couple affects every point on the object equally. Because I'm applying the couple on that nut on the left, but I'm spinning the wheel about the central, it's about the axle basically, okay? The hub, all right? Y'all good with that, okay? So you know what, you start to turn, you break those nuts before you lift the wheel, right? That works better, okay? All right. And now here's just an example. Some of my fine woodwork that I do here sometimes. That's some siding off my house. I had some problems, but here we go. I can apply couples. Now what I can do, I can hold this thing in the back. I have a little axle back there. I can twist this handle, and I'll just turn it. See, I'm not applying the twist about that central bolt. I'm applying it at the handle. Same thing with this wing nut. I can twist the wing nut, but I spin the board, okay? That's what's going on there. So I can apply a regular kind of curve couple like that. I can also do like a double couple like that, and I spin everything about this central axle, okay? So what's happening is I'm twisting the entire object. Every point on the object feels that couple. That's the idea. Okay. So we good with that? That's kind of a funny thing about these.